we are going to be talking about gases, and in order to introduce this topic, we need to start with the kinetic molecular theory. It is best to view the gases as molecules, as shown by this application. And whenever you can, throughout this chapter, you should be trying to imagine gases, as you can see here, as essentially spheres or molecules moving in straight lines, straight random lines, with bouncing off the edges. And if you do this, it will make everything easier. Now, there are three main assumptions that we have. The first assumption is that the size of the particles of a gas is negligible compared to the volume of the container that they are filling. Okay, and essentially this means that if you take the size of each particle, the diameter, the area, the volume of each particle, and you combine all of them, and you compare it to the volume of the container that they're in, the volume of the particles would be so tiny compared to the volume of that they contain that we ignore it. So all of the gas laws and the equations that we derive and we use in this chapter, we don't take into consideration the volume of the particles themselves. Now, the second assumption is that the average kinetic energy of the particles of the gas is proportional to the temperature in Kelvin. Now, this basically means that as the temperature increases, the velocity of the particles and the kinetic energy of the particles will increase. Okay, so as you can see here, the temperature is 373 Kelvin. If I increase the temperature up, you will see that the particles are now moving a lot faster than they were earlier. If I would decrease the temperature, you can see the particles suddenly lose energy and they become slower. Okay, so if I move it back up, you can see they're moving fast. Okay, now temperature is a measure of the mean average kinetic energy of the sample. So some particles will be moving faster, some will be moving slower, and the average is basically translated to the temperature that you see. Now, if we have a mixture of different gases within the container, for example, I'm going to put some krypton in here, okay? Basically what will happen is that you can see that the krypton purple spheres are moving slowly compared to the helium. And that's because even though the kinetic energy of both are the same, so it's important to note that krypton and helium here, they have the same kinetic energy. But the krypton is heavier, and therefore it must move slower in order for it to have the same kinetic energy, because kinetic energy is equal to half mv squared. So if the mass is greater, in order for the kinetic energy to be the same, the velocity must be lower in order to keep the kinetic energy the same as the helium particles. Now, the helium particles on average will have the same kinetic energy, but because their mass is lower, the velocity must be higher in order to have the same kinetic energy that the krypton particles have, as you can see here. And the last assumption that we have are that all collisions are elastic within a gas sample. As you can see here, when there's a collision, the molecules, the kinetic energy of the molecules is conserved.